SoundCheck has been the leading production audio test system for hundreds of transducer manufacturers around the world for over 25 years. With its sophisticated suite of audio measurement algorithms that offer precise measurement, fast throughput, excellent noise immunity, and world-class reliability, it's easy to see why it's a popular choice. As the products we test have evolved from simple transducers to complex systems, so too have factory automation systems. These days, many factories use large, highly customized, integrated test configurations to evaluate products. And not only for audio, but often video, visual, and other performance defects. And while basic audio tests can usually be programmed in whatever language your test system is built on, the many years of audio expertise that has gone into Listen's algorithms is virtually impossible to replicate. Not to mention the massive cost, both in terms of expertise as well as ongoing maintenance. And certainly, when you get into some of the tests needed for complex modern devices, that kind of thing is not easily recreated in simple code. So what we've done is given you the tools to easily integrate SoundCheck into your test system. Our philosophy has always been to offer the best flexibility to work with whatever you already have in place. If you already use SoundCheck, you know that you can use it with any hardware. Any microphone, any coupler, or even any audio interface. This now includes any test environment that can provide TCP/IP commands. This means that SoundCheck can be controlled using any compatible programming language, including Python, C, LabVIEW, or even Matlab if you're in an R&D environment. This makes it easy to integrate SoundCheck test systems into your overall factory test system, no matter how large or complex it is. And we're not just talking about basic open, start, or stop controls either. We've greatly expanded the control options, so in addition to simple applications where you can open SoundCheck, run a sequence, and log the results, you can now also pass data, curves, waveforms, variables, and other commands in and out of SoundCheck. This opens up a huge amount of flexibility for streamlining and executing tests. What I'm going to do in this seminar is show you some of the examples of the types of things we can do in SoundCheck with external control. And as you know, every automation system is different, so I'm going to focus on the different ways you can get commands and data in and out of SoundCheck, as well as the tools we provide to help you do this. We'll give you some example use cases along the way. This should help at least give you an idea of how external controls work with SoundCheck and get you thinking about how it can work for you. First, I'm going to show you how we enable TCP/IP in SoundCheck and walk through the commands that can be used. I'll also show where you can find example code in different languages. My colleague, Pranav, will then give you a quick walkthrough of a SoundCheck test sequence. We'll then go on and use external control to interact with that test sequence. We'll show you external control in its simplest form, that's opening up and running a sequence in SoundCheck using a Python script. You can also return the data for use in whatever application that you want. Then, we'll show you how to change test parameters via external control. And this is where you really start to see the benefits of TCP/IP control. In high throughput environments, for example, test conditions on the fly can be adapted for different products, which gives you a huge amount of flexibility and can actually simplify your test procedures. Next, we'll demonstrate how to load a test signal onto a device under test. In this case, we'll use an Android phone using a custom step in a SoundCheck sequence. This is applications anytime you're using a device that supports external control, as you could tell it to play a test signal, adjust volume, etc., all directly from SoundCheck. I'll show you how we can use external control to automatically equalize WAV files loaded into SoundCheck via TCP/IP on the fly. And this allows using SoundCheck's calibrated signal paths on any WAV file. This makes applications where multiple speech or background WAV files need to be played out of an equalized source much simpler. Finally, for R&D applications, we'll look at using Matlab with SoundCheck. So now we're going to take a look at actually sending TCP/IP commands to SoundCheck. The first thing we'll do is in SoundCheck, in Edit Preferences under the Advanced tab, make sure that we've enabled the TCP/IP server. That way we're able to send and receive commands. So Preferences, Advanced. We need to make sure that this checkbox down here is enabled. We also need to pick a port. So by default, we've arbitrarily chosen 4444. If you don't have a reason to change that, I'd recommend leaving it the same because all of our example code will use this port. We're enabled here. I'll click OK. And now if we look in Windows Explorer, in the SoundCheck folder, there's another directory called External Control Examples. In here, we have some example code for different languages. And again, these languages aren't required to use with SoundCheck. These are just common ones that we've built applications for. Any language that can talk via TCP/IP can be used with SoundCheck. The first thing we're going to look at is the LabVIEW example. If we click in this folder, you see we have the source code available as well as the full application. So I'm going to open the application over here and we'll take a look at a couple of the commands. When we first open this at the top, we'll see we're connected to a server IP address of localhost, which is the computer I'm running on port 4444. If I wanted to connect to a different computer over the network, or if I change the port in my preferences, I could edit it in here and connect to that computer. The rest of the commands down here are exactly what we saw in the command set definition. Anything that we could run is available to select here. So if I wanted to get the status of SoundCheck, I could click on this command and then down here, execute it. The bottom right will show us the full response JSON. So this will tell us if the command completed, as well as anything that we're actually interested in back from the step. So this get status option is looking to see if SoundCheck is busy. It currently isn't, it's a false. So here is again everything that we could select, something like running the sequence, opening it. If we did something like looking at the serial number over here, I can run a command called soundcheck.setSerialNumber. Now there's a parameter I can enter here. So if I enter the string SN123, when we look at SoundCheck, we can see the serial number up here is currently blank. And if I execute this command, it's going to set my serial number here. In the other direction, we can use soundcheck.getSerialNumber. And when I execute this, we'll see the response JSON will have the return data that includes the string of my serial number. So again, it reads the SN123 from SoundCheck. This application is really good for seeing the commands available to communicate via TCP/IP with SoundCheck. It's helpful to see which ones you can use, which ones might be useful, but it's not really great for actually testing anything. For that, we're going to hand it over to Pranav, who will write us a SoundCheck sequence and do some actual application work using Python.
So what I'm going to show you now is how to run sequences from an external program or a script like a Python script using TCP/IP. So before I do that, let me quickly show you what my hardware setup looks like. I have an AmpConnect 621, which is a 6 input, 2 output audio interface, which comes with a built-in microphone preamp and an amplifier to power the loudspeakers. So I'm using an SCM3 microphone connected to input 1 of my audio interface, and the amplifier outputs are going into this Cambridge audio loudspeaker. So we provide a bunch of example sequences for our customers inside the SoundCheck installation directory, sequences folder, and I'm using one of the sequences from that folder called complete test using AmpConnect 621, which will basically measure the frequency response, THD, rub and buzz, impedance, and also calculate the average sensitivity value at 1 kHz. So let me quickly open the sequence, go to my sequence editor, and walk you through the different steps that are in the sequence. So the sequence starts with a bunch of message steps where you can set different parameters, voltage biases for my AmpConnect 621. I can also set levels to be used in my stimulus step. And then we have a stimulus step wherein I'm using a 12th and 3rd octave sweep. So the stimulus step is actually going to create the stimulus inside the memory list. And then when I have an acquisition step, I can actually play that stimulus which is already created in my memory list through the speakers and record simultaneously through my microphone. So once I have the recorded time waveform, I can have a bunch of analysis steps. So the first analysis step is basically comparing the sweep stimulus with the recorded time waveform and calculating the transfer function or an FFT to get the frequency response. Then we also have THD and rub and bus. We also have an analysis step to calculate the impedance. The 621 in particular has a built-in resistor for impedance measurements. And then I also have a post-processing step where I calculate the curve average of the frequency response at 1 kHz to find average sensitivity value. We can also have limit steps inside a sequence. I have a limit step for average sensitivity where I can select upper limits and lower limits for my average sensitivity value. Currently, I have them set to 100 dB and 90 dB. I can have limit steps for my response as well, where I can have an upper limit curve and lower limit curve. Finally, I have a display step where I can display all the information on an XY graph or a display window. So let me quickly run this sequence. So when I run the sequence, it gives me the fundamental curve, the impedance curve, THD and rub and bus, average sensitivity, polarity, response margin, and make sure if all of these calculated parameters are within the limits. So let's say I would like to run the sequence through TCP/IP using a Python script. How do I do that? For that, I created an example script. Let me open the script and walk you through the different stages. So as Mark mentioned before, we provide a list of command set definitions in different languages, in Python, C, C#, Matlab, etc. And the script starts with importing a bunch of dependencies that are needed for this script to run. And then we construct an installer and launch SoundCheck, go to the sequence path, and then open the complete test sequence from that path. We can also set lot number. For example, I'm setting lot number here as 1234. I can set serial number as well. And I can run the sequence using sc.runSequence command. And once the sequence is run, I can print the results and get a particular curve. In this case, I'm getting back the fundamental curve as a JSON string. Let me actually open command prompt and run the script. I am right now at the working directory, which is C, SoundCheck 20, external control examples, Python scripts. I'm going to type in Python demo1.py and hit the enter button. So what this is going to do is launch SoundCheck, set the lot number as 1234, open the complete test sequence from the path that we provided, run the sequence, and get back the fundamental curve as a JSON string. So there we go. These are the displays from inside SoundCheck, and we got back the JSON string of the fundamental curve. Another good thing about SoundCheck is that you can run the sequence entirely with SoundCheck in hidden mode, so you do not see SoundCheck at all, but you can still get back results onto your command prompt as JSON strings. And you can further process this data once you have the string, and you can also save it to a database.
One other benefit of using TCP/IP is we can change some parameters on the fly. If we look in this sequence and double-click on Overall Sequence, there's this sequence parameters section. Here, I've defined an upper limit for a curve, and then a test level, start frequency, and stop frequency for a value. By adding these in here, what we're doing is creating blank memory list items. So here under curves, I can see the upper limit I defined, and under values, the level as well as the start and the stop frequency. So why is this helpful? For example, in the stimulus step, what I'm doing is using these memory list items to define how I'm sweeping, what range I'm sweeping at, as well as the level. So now using another program, I could set these values via TCP/IP to change what level and frequencies I'm playing across. If we look here in the Python script, down in this section, we can see that I'm setting a value. That's the test level, and then the start frequency and stop frequency, as well as setting a curve. That's the upper limit. So using the sequence parameters, I'm able to create these blank templates, and then through my external control, I'm able to set them whatever I want on the fly. So what does it look like when we actually run this script? So here, if I run Python demo 3, there's actually a help option, and this will show us all of the commands. So how I would actually enter the level, the start and the stop frequencies, as well as some other options. So as an example, let's run this, and I'll choose a level of -10 dBV, a start frequency of 100 Hertz, a stop frequency of 10,000 Hertz, and then we'll set the limit at 30. When I run this, you'll see that the values will be set to SoundCheck. We'll hear a sweep from 100 Hertz to 10K with a limit of 30 Pascal per volts. So here's my graph. 100 to 10K, limit of 30 Pascals per volts. Shows me it passed. Now I want to run this again, and I can choose some different values. So instead of -10, we'll put in 0. And now let's sweep from high to low. I'll do 20K to 50 Hertz. And this time I'll set the limit at 15. So we saw the graph before, it was 30 Pascals per volts. Now it should be a limit of 15, sweeping from 20K to 50 Hertz. Great. So this method that we can use to set these different parameters, instead of having to type them in through the command line, we could instead take values from a list. Maybe we'd import a CSV. We could increment levels, so if I wanted to play the same sequence but loop a test level, all of this would be possible using a simple script. Another option would be to use loops directly in SoundCheck. We could use loops in the sequence directly and then control the sequence through TCP/IP. A great example of this is in the SoundCheck folder under Sequences, How-To Examples, called Loop Stimulus Level. Directly in the SoundCheck sequence, we can iterate and increase the level during the test, and then we could use external control to just run the sequence. In the last example, we looked at how you could set different parameters via the command line as arguments. So that's very interesting in theory, but we're not going to have people on the production line or actually operators manually typing in these limits. So what we're going to look at now is a way to expand on that. So in the sequence I have open here, I have an upper and lower limit set in my sequence parameters. So we're creating blank curves that we'll be able to write via a Python script. But what we can do instead of manually typing them in is we're actually going to import them in from an Excel sheet. So if we look over here, this sheet will actually contain an upper and lower frequency response for two different devices. So the first column will define the device type. So we could choose device A or device B. Device A has an upper and lower limit, and device B has its own upper and lower limit. So now when we run the script, we could choose, do I want my limits for device A or device B? What we're going to run here is demo number 4. And instead of having to enter this stuff in through the command line, we're actually going to have a GUI pop up. And this is something when we're actually doing some testing in the real world, this is what we'd recommend configuring. Your users don't want to open up command lines. You're not going to be typing things. We can just create some sort of GUI. All they have to do is choose which device they're going to run. You could set the serial number this way. You could set the test level, limits. And when they select which one they're running, in the background, we can set these values via external control. So here, I choose device A, and it's just going to pull in those limits. All right, and we can see I have my device A limits across the frequency response. These might not be appropriate, so instead I'll choose my device B limits. Run it again. And there we go. This is device B. These limits make sense, so we now get a pass. So this method will allow us to add a lot more complicated items via TCP/IP. And again, we could create a GUI that makes all of these easily selectable. We don't even need to see SoundCheck in the background. It's very common to run SoundCheck completely hidden. All you would do, for the operator's point of view, is choose which device you're testing, and it could even be part of a larger test suite, where only one small section is the audio.
Alright, so what I'm going to show you right now is how you can make use of custom steps inside a sequence to send commands to an external device, for example, an Android phone. SoundCheck has these step templates called custom steps, which you can make use of, similar to the other step templates that we provide, and one of them is named the system custom step. So what is a system custom step? A system custom step allows you to execute commands very similar to how you would do it on command prompt or terminal from inside SoundCheck. So this is how it looks like. You can type in a command that you would normally execute from command prompt or terminal, and you would set the working directory, and what you would do is SoundCheck will execute those commands when it runs the sequence. So here I am testing an Android phone, and I would like to look at the RTA when I play a WAV file through it. So the setup is pretty similar. The phone is connected to my computer using a USB cable, and I've connected an SCM3 microphone to input 1 of this audio interface, which is an AmpConnect 621. Since I'm testing an Android phone, Google provides this SDK called ADB, which is Android Debug Bridge, which allows me to send commands to my Android phone without physically contacting the device. So here's a sequence that makes use of custom system steps and send commands to the device using ADB. So I have 3 custom system steps in the sequence. So if I open the first one, I see that what it is doing is basically push a sample.wav file from my SoundCheck 20 WAV files directory onto my phone. And once this is completed, the second custom system step will play that WAV file through the phone, and simultaneously we are using an acquisition step with an RTA virtual instrument, which will give you the RTA of the audio while it is playing back. And then we have another custom system step which will remove the file from the device once we are done with the analysis, and finally display the RTA on an XY graph. Another thing to note about custom system step is, as you can see on the left side, we provide a bunch of custom step templates that you can use in a sequence, and there is also a mixer volume step template that is included with SoundCheck. So this is particularly helpful if you would like to change the volume of a device within a sequence. You can set the device name here and change the volume by percentage, and that will be affected within the sequence. So now let's come back to this original sequence to test the phone speaker, and let me run the sequence.
The shelves were bare of both jam or crackers. A joy to every child is the swan boat.
The stems of the tall glasses cracked and broke. The wall phone rang loud and often.
There you go. So here's the RTA of the audio file that we just played through the speaker. So you can insert this custom mixer volume step into your sequence, and that will change the volume of the device in the middle of the sequence.
Another really helpful thing to do using TCP/IP is to play back equalized WAV files from disk. So in SoundCheck, using the sequence parameter of a waveform, we're able to define this placeholder that I called stimulus. And then in a new step type called memory list waveform, we can take this stimulus waveform and define it out of our source speaker at 94 dB SPL equalized. So why is this useful? Using an external program with TCP/IP, I could take a number of WAV files and set them as my stimulus. Regardless of what level the scaling is on the digital WAV file, this stimulus step will make sure all of them are played back out of my source speaker at the appropriate level with an EQ curve on it. Over here, we created Python demo 5, and what this will take as an input is a directory full of WAV files. It then will iterate through every file inside of that folder, set it via TCP/IP. That will go through our stimulus step to make sure it's equalized and played at the appropriate level. Here I have a speech files folder. This just contains 3 speech files, but this is really useful for things like background noise. If we're using a smart device, maybe we'll need to have wake word enabled WAV files in here, or just a number of different test signals. So I'll drag this in here. When I run this script, it will play 3 different WAV files at 94 dB SPL, equalized for this source speaker at the location of my device under test.
The last switch cannot be turned off.
It's easy to tell the depth of a well.
4 hours of steady work faced us.
And there we go. This was only 3, but you can see how much easier it would be to run hundreds of different WAV files through SoundCheck and get an equalized output by using external control. So as you can see, there are many ways that external control is valuable in a manufacturing environment, as it enables you to take advantage of all the benefits of SoundCheck, yet fully integrate it and automate it with your test environment. Hopefully we've given you some ideas of how SoundCheck can be incorporated, and we're always happy to talk offline if you have any questions about your specific use case. I just want to end with one final demo for the R&D users among you. Although pretty much all R&D functionality is simplest when implemented within SoundCheck, I know there's some research environments that are die-hard Matlab users, and we do offer full integration and control with Matlab too. In this demo, my colleague Rahul is going to show you an example of controlling SoundCheck with Matlab and saving measurement data to a .mat file.
Hi, I'm Rahul, Senior DSP Engineer here at Listen. Let me show you a quick example of using Matlab to control SoundCheck. Here I've created a simple script in Matlab to open SoundCheck and run the sequence complete test. This sequence saves a .mat file, which we will then load in Matlab and create some graphs. First, we will open SoundCheck from Matlab and connect to it using TCP/IP. We send SoundCheck some commands to open the complete test sequence and run it. In this sequence, the data is automatically saved to a .mat file using an autosave step at the end of the sequence. The script then closes SoundCheck and loads the .mat file into Matlab. Now that the sequence data is in Matlab, we can graph the data.
So as you can see, there are many ways that external control is valuable in a manufacturing and R&D environment, as it enables you to take advantage of all the benefits of SoundCheck, yet fully integrate it and automate it with your test environment. Hopefully we've given you some ideas of how SoundCheck can be incorporated, and we're always happy to talk offline if you have any questions about your specific use case. I hope you found this presentation on external control with SoundCheck useful. Thanks for attending.